Okay. All right, everyone. I think we'll kind of officially kick off the webinar. People can continue to introduce themselves in the chat. As you know, my name is Mary Dussault, and I am here at the Smithsonian Astrophysical Observatory with Erica Wright, also on the Universe of Learning team. And as always, we have our colleagues at Space Telescope, the lead institution for the Universe of Learning program, Tim Rue and Brandon.
She's downstairs, so...
Okay, I'm gonna take a moment to mute folks here so we get started. And also our affiliate team, Patty is on the line, and you all know Caroline and Christina, who are also part of this Universe of Learning partnership. And during today's webinar, we're very excited to have a guest scientist, Tiffany Kataria, talking about her exoplanet research and giving us a little insight. And so, Tiffany, welcome to you, and she'll be giving us some interesting insights a little bit later. And I wanted to, so the scope of today's webinar, we're going to do a little bit of historical background about imagining other worlds. Really the bulk of the science background is going to be around detection methods. Tiffany's going to talk to us about our learning about exoplanets from hot Jupiters to super Earths, and then we'll go over resources. I did want to, before we start, bring up the poll results. And it looks like we have a fair diversity of opinion around the question, are we alone? But practically none of you thinks we're all there is. And this could be somewhat different than it was 20 years ago, but it looks like there's more consensus around there's probably life out there, not sure about intelligent life. And here's the spread of when you think we'll find signs of life beyond Earth. So Tiffany, when you present, I'll be interested in your opinion on that as well. Okay, so a little bit of background about this question, are we alone? Obviously, it's one of those questions that is universal, a human question. You look up in those stars and you think, are we the only ones here? Could there be other worlds? And, you know, we don't know what a lot of cultures around the globe thought about this question. We do have some writings from the early Greeks. Epicurus thought there were other worlds. More recently, in the 16th century, Giordano Bruno, who was an Italian philosopher, had a lot of thoughts about other worlds. And here's a quote from one of his writings. In space, there are countless constellations, suns, and planets. We see only the suns because they give light. The planets remain invisible, for they are small and dark. There are also numberless Earths circling around their suns. And so here's a very early idea of extrasolar planetary systems. Now, Giordano Bruno had lots of other ideas that were contrary to the Catholic doctrine of the day, and in fact, during the Inquisition, he was burned at the stake for, we're not quite sure which of these beliefs, but in the year 1600. Later that century, in the 17th century, Bernard de la Fontenelle, a French philosopher and scientist, also thought that there must be worlds circling the other stars. And so, but no one had any data about this. In fact, for thousands of years, we knew about first the 5 planets, Mercury, Venus, Mars, Jupiter, and Saturn. Earth wasn't considered a planet in the same way. Those were out there in the heavenly sphere. And of course, we had 9 planets once we discovered Pluto, and it became more or less. But now we know of not only the planets in our own solar system, but worlds around other stars. And in fact, I checked this morning on the exoplanets.nasa.gov site, and it registered 3,532 confirmed exoplanets discovered in over 2,600 star systems. We now know that on average, each star has at least 1 planet around it, and 1 in 6 of the stars, when you just look up in the sky, is likely to have an Earth-sized planet around it. Now, Earth-sized is different than Earth-like, and that's one of the things we'll be talking about as we go along. But a key finding over this last 20 years of exoplanet discovery is that other worlds are not like ours. We started looking out, expecting solar systems to be like our solar system, with small planets near the sun and large planets far away from the sun. And these solar systems are quite different than ours, and we'll look at some of that. But what we want to talk about today is detection methods. How do we know that these planets are out there? The slide on the screen, by the way, is an artist's imagining. Again, Giordano Bruno, 400 years ago, is imagining what other worlds might be like. And here is a more scientifically based imagining of what it might be like on one of the worlds of the TRAPPIST-1 system. If you were to look out, and you'd see these other stars actually in the sky. So how do we find these planets? How have we found 3,500 or more planets and another 5,000 candidates to be planets? Well, I'm actually going to bring this website right into the screen and demonstrate. But I wanted to mention that the slide deck that we usually share on the Universe of Learning portal for all of you will actually have more information and some examples of what the real data looks like, but I'm not going to highlight those. I think I'll just use the actual interactive website to talk about our techniques for finding a planet. And so let me put that in here and enter full screen, 5 ways to find a planet. So the first way, and actually, sorry about that, before I look at this, I'm going to, I did want to note that here's a graph of planet discoveries over the last couple decades, and you can see that the graph kind of starts right here around 1995, which was the first planet found around a sun-like star, and it was using this method we're about to talk about called radial velocity, which all the detections found by that are in this pink. And then you start to see this booming number of planets found by the transit method, which we'll also talk about. And that really starts increasing right here after the launch of the Kepler mission. So we'll talk about that as well. But this radial velocity method is also known as the wobble method. And essentially, when you have a star going around a planet, it its gravity tugs at the planet, and that tugging makes the planet move, wobble a little bit towards and away from us. And as it wobbles towards and away from us, we can see the light shift a little bit to the red when it moves away from us, and a little bit to the blue when it moves towards us. And this is a very similar, actually a great demonstration of this that a lot of science centers do for this, this wobble when something is spinning around and wobbling towards and away from you, is if you swing one of these corrugated tubes over your head, and you hear the wow, wow, wow Doppler of that going back and forth. That's an analogy for the signal that exoplanet hunters detect using this method, looking at the light very carefully, the spectra, the spread out light from a planet going around a star. And this method helps you know the mass of the planet, because you can measure the amount of gravity between the star and the planet by the strength of that wobble. But you don't know whether it's a really dense planet, a tiny planet with a lot of mass, or whether it's a big planet with a lot of mass. You only know that it has a lot of mass or a little mass. So that's the first method. The transit method, which has now produced the most number of planets. You can see here 2,752 planets discovered. Is the method that the Kepler mission, NASA's Kepler mission uses. And essentially, if a planetary system happens to be lined up so that it's edge on to our view, when a planet goes in front of its host star, we see that host star dim just a little bit. We don't resolve the actual orbit as you do in this animation. All we really do is see the signal of light dimming, which you can see in this little animated graph on the left. And different planet sizes can be detected by the amount of the dip. Because if it's a big planet, it's covering up a lot of its star's light, and the star dims by quite a bit. If it's a little planet, it's not covering up so much of the star's light, and it dims less. And you can directly figure out the size of the planet. So here's a case where with the wobble method, you can figure out the mass, but you don't know the size. And with the transit method, you can figure out the size, but you don't necessarily know the mass of the planet. So both of those together are really what exoplanet researchers want to have the data on, because once they know the size and the mass, then they can actually figure out the density and figure out if it's a rocky planet or a water world or a gas planet. And that's very important information to have. So those are the two most popular detection methods. But another method, which is what most people might naively think is probably the most direct method of detecting planets, is to take a picture of them, direct imaging. But it turns out this is very difficult because the planets, the stars are very far away. If you'll remember from our size and scale webinar, the planets, the stars are very far away, and very bright compared to the planets that are going around them. So it's very hard to make out the dim little signal from the reflection of that planet that's not even emitting its own light and optical. It's only emitting maybe some infrared light. So the technique to do direct imaging is to basically simulate an eclipse, to have all kinds of instruments that try to cover up the light coming from the star with a coronagraph or some sort of device in order to be able to pick out the dim light coming from the planet that might be around that star. As you see here, there's about 44 planets that have been discovered that way. This fourth way that I'm going to talk about is uses this feature of matter bending space and time that I think we actually talked about with gravitational lensing and galaxies on an earlier webinar. But what you want to pay attention to in this animation is there's a distant star in the background. Here's Earth in the foreground, right, this little blue dot. And here is a star passing through our field of view with a little planet going around it. And as it passes through our field of view, the gravitational lens, the bending of space, makes that star in the background brighten just a little bit, and then the planet brighten just a little bit more than that. So look at this signal here. There's the star, whoops, there's the planet, and there's the star. So this is the microlens event, and this is the lensing of the star itself. So these are 4 methods that are used. There are a number of other methods that you can explore on this website, but I'm going to go back to our slideshow at this point. All right. Let me go through those slides. So again, that wobble method, this is what real data looks like. You read off the velocity that star is wiggling away and towards you, 10 meters per second, toward you, away from you, toward you, away from you. And over the time we've been detecting planets, techniques have gotten better and more precise to measure. The first planets were quite big because, of course, you can detect a better wobble if you have a bigger planet. And you can also detect a bigger dip if you have a bigger planet. So for a while, we only had hot Jupiters, but as time went on, and especially with the Kepler mission, we've started to detect Earth-sized planets. There's that microlensing event. This is what the real data looks like of a star going through the field, and then a little micro blip of a planet that was going around the star, lensing some light. Here's a actual direct imaging method. This is a Hubble infrared observation of Fomalhaut, which is actually naked eye star. And here the data is from the stars being obscured, and you see a little dot that's going around that star at quite a distance from it. And the transit method, this is what real transit data looks like, where you're measuring the brightness of a star, and every once in a while the brightness dips, dips. This is a star system with 7 planets going around it, and you can see the brightness keeps dipping. So that's what the real data looks like. And again, with the transit method, more recently we're getting down to be able to detect Earth-sized stars, Earth-sized planets. And that's primarily due to the Kepler mission, which I'm going to space out when it was launched. Maybe Brandon or Tim could type that in or remind me when that was launched.
We have our subject matter expert here, I think.
Tiffany, when was Kepler launched?
I believe it was 2009.
Yes, okay. I think right. So so that graph you saw early in the slide showed suddenly a burgeoning of extrasolar planet detections after Kepler was launched. And Kepler really was launched in order to establish the statistics. It stared at one place in the sky for several years, looking at over 100,000 stars, and really gathering statistics about how frequently do stars have planets going around them. And I couldn't find a more recent diagram of this, but this is pretty representative, that basically when we look out at the planets we've detected, most of the planets we've detected are not like planets in the solar system. So there's this big chunk of planets that are bigger than Earth but smaller than Neptune, and those appear to be the most frequent kinds of planets in the galaxy, or at least as detected by Kepler. So that's a really interesting thing about having detected these planets. And as we mentioned, they run from being giant Jupiters that are very close to their stars to rocky planets that may or may not be in the habitable zone of their planets. I'm going to show a couple of slides. This next one, which is another plot of data, is a little tricky to parse out, but what it does is show that we have collected lots of statistics around these are the different methods, the different colors. So we have the wobble method. We again, the duration of the planet year is related to how far out the planet is, right? If its year is longer, here's Earth. Our year is about 300 days. And so the wobble method really detects things closer in, because again, to have enough gravity, a gravitational force to tug that star, that works a lot better when a planet is closer into its star. And the red here are transits, and you can see we have from very close in planets all the way out to planets that are very big, multiple Jupiter masses, and far out. But it's really hard to get down here where there's small rocky planets like Earth. So Kepler really helped us understand that almost every star, when you look in the sky, has at least a planet around it, and that 1 in 6 or maybe even more of those stars are likely to have a Earth-size or super-Earth planet around it. But the stars that Kepler looked at were, in general, pretty far away. And so I want to describe the difference between the Kepler mission and an upcoming mission that's going to be launching next year, which is the TESS mission, and extrasolar planet researchers are excited about that. So this slide shows, oops, somehow I lost my, I lost the annotations of what TESS does on this slide, so I'll have to point it out. The Kepler mission stared in one direction and detected planets around stars, most of which were pretty far away, maybe 1,000 light years away, or 500 light years away to 3,000 light years away. TESS, on the other hand, is going to look over the whole sky around us about nearby bright stars, so maybe a couple of 100 light years out, and look at much more nearby stars. So the reason for that is, once you detect these planets going around nearer, brighter stars, you can also get their wobble it's much easier with a brighter star to measure this radial velocity wobble due to the presence of that planet. And then we can get much more information about what those planets might be like. So here, for example, is the current census of potentially habitable exoplanets ranked by distance from Earth in light years. And you can see we only have, less than a dozen detected exoplanets that are close by our solar system, close by Earth, less than 40 light years. So all those thousands of planets that Kepler has detected are quite far away, and TESS aims to discover thousands, and in fact tens of thousands of planets much nearer to us. This is a map of the anticipated discoveries from the TESS mission. This is a sky map, so it's kind of as if you took the dome of the sky around you and flattened it on the paper. And the red dots are a couple of 100,000 pre-selected stars. The blue dots are just stars in the field, of which there are millions, and so TESS could make a lot of exoplanet discoveries. The way it's built, most those discoveries, what we're really looking for is these smaller planets that might be more Earth-like. And because TESS is surveying all these nearby planets and brighter planets, it's anticipated that it may find over 500 planets that are in the size range where they might be rocky and be habitable. This slide just shows kind of a comparison between the Kepler stars. The fainter stars are towards the bottom of this plot. And so these are Kepler stars, and these are the stars that TESS is going to find. And again, this is all around this desire to be able to detect both the size of the planet from that dip, from that transit method, and the mass of the planet from the wobble. So TESS is going to detect all these transiting planets, but then it's going to need follow-up, a lot of follow-up to start to characterize those planets. So wanted to, oops, I went one ahead here. Hubble, Spitzer, and Kepler have all made discoveries about exoplanets. Upcoming in 2018 is the TESS mission, which will really pave the way for the James Webb Space Telescope to do follow-up on those planets. After James Webb, there's a mission called WFIRST. And Brandon, I don't know if you wanted to talk a little bit about this arc of future missions. I know that Tiffany's going to talk about it as well, but...
Yeah, I'll just, because Tiffany's going to talk about it, I think I won't say too much. Other than WFIRST is, so Webb is slated for 2019 launch. WFIRST is slated for the mid-2020s. And then there are, as Tiffany will talk to you later, there are other conceptual missions beyond WFIRST that people are considering. Did you want me to talk to this one too? Okay. Yes. So, so I think this is our last slide before we turn it over. So
one more.
Oh, one more.
Yeah.
Okay, sorry, getting ahead of myself. All right. So the WFIRST mission, the Wide Field Infrared Survey Telescope. Everybody has to have an acronym. All right. So WFIRST is quite an amazing telescope. It's basically a Hubble class telescope, or a Hubble size in terms of its mirror telescope, but it's a survey telescope, so it's going to survey the whole sky. It's going to do some visible, but a lot of infrared. That's hence the infrared survey telescope, near infrared. And again, surveying the whole sky is going to be very valuable. You imagine those really beautiful Hubble images, but across the whole sky, or almost the whole sky. This plot here just basically shows you the space or the types of planets that WFIRST may be able to detect. Now, WFIRST has two main instruments on it. It has a wide field imager. That's the survey instrument. It also has another instrument, a coronagraph, and I believe Tiffany will talk more about that. But just for detecting exoplanets, the wide field imager is going to do a lot. So in this plot here, what you see on the x-axis is what's called semi-major axis in AU. That is the distance that the planet resides from its host star. You'll notice Earth is at 1 AU. That's how the astronomical unit is defined. It's defined from the distance from the Earth to the Sun, hence that's why it's 1. So a planet that is 10 AU is 10 times the distance to its star as Earth is from our Sun. And so that's sort of a distance from the host star. And then on the y-axis, you have planet mass in Earth masses. So everything here is scaled relative to Earth. So 1, again, is Earth. So if you look at 1, 1 on the plot, you're going to find Earth. And thankfully, whoever made this plot put the other solar system bodies on here as well. What you're going to notice is that WFIRST is going to find a lot of these planets that reside a little further from their stars. And that's really powerful because, again, with the transit technique and with the wobble technique, it's much easier to find planets that are close to their stars because you need to see multiple transits to be able to to determine that it's actually a planet, or you need multiple wobbles. But with microlensing, you don't need that. So you can find planets that reside further from their host stars. It's really going to fill in a big gap in our understanding. Even to the point where if you look on the right, there's free-floating planets. There have been, I believe, less, like maybe a handful of these that have been detected, but WFIRST is going to blow this out of the water. So it's going to be able to detect what you might call rogue exoplanets, planets that do not have a star at all. And these things should be drifting about our galaxy as well. And the last point I'll make on this is that there is one more detection technique that we ran out of time, so we didn't go over. But if you go back and you look at astrometry, astrometry is one more detection technique. WFIRST may be able to find exoplanets in that technique as well. And astrometry is just basically looking at the actual lateral motion of a star on the sky, its physical appearance, its motion changing on the sky because a planet is circling around it. So the gravity is making it. This is different than that wobble or Doppler technique where you're looking at more of a Doppler effect. So with that, go to the...
Okay, and so the goal, the ultimate goal, the big goal of all this finding planets is ultimately to be able to figure out what they're like. And JWST will take a first crack at this by looking at the spectra of planets, or the light. Here is an example of a spectra broken up by wavelength. But this is a kind of a future goal in terms of being able to characterize planets. And that whole idea, where I think it's time to introduce Tiffany to tell us a little bit about from hot Jupiters to super Earths, a little bit about the weather around planets and how we find those things. So Dr. Tiffany Kataria, I'm going to stop my sharing so that you can share your screen.
Okay, great. So let's see, let me close there. Okay, share screen. Okay, can everyone see my slide here?
Yes.
Is that all right? Great. All right. Well, thanks everyone for having me. It's really nice seeing, well, people from around the country participating. I actually spent a summer in Houston as a research intern at the Lunar and Planetary Institute, so shout out to LPI, shout out to Houston. Yeah, so today I'm excited to talk to you about some research that I've been doing, in particular understanding weather on extrasolar planets. And you might think, arguably, maybe it's overkill. Why would you need to know the 3D structure of an atmosphere? I mean, there are point sources that are many, many light years away. Can we really learn that much about an atmosphere or a planet that's so far? But in fact, the data is showing us that we can really extract quite a lot of information about these distant worlds. And so that's really exciting. And so I'll kind of present a very high-level overview of, kind of the status of the field and some highlights and kind of where we're at and where we're going. All right, so Mary already motivated this really nicely, so I won't belabor these points, but except to say that I think now exoplanet science is an era of not only detection, but also characterization. And so Mary showed a similar plot earlier, so this is, again, exoplanets discovered by year. And so over the past couple of years, exoplanet discoveries have really boomed, and this is in large part due to Kepler. And so again, I wanted to highlight a particularly exciting result from the TRAPPIST-1 system. And so this is a system of 7 roughly Earth-sized planets orbiting an ultra-cool dwarf. And the reason this particular system and other systems we've observed, we focus on perhaps smaller stars is because essentially for a transiting exoplanet, you're measuring the radius of the planet relative to the radius of the star. And so it's easier to measure, bigger signals. So you want a larger ratio. And so that's why smaller stars compared to smaller planets. And so TRAPPIST-1, the planets orbit this ultra-cool dwarf, and a lot of other Earth-sized planets that we've discovered so far fall in that same regime. But I think TRAPPIST in particular, given that it was 7 Earth-sized planets, I think it really captured the imagination of the community. And this is actually, I think, one of my favorite travel posters that NASA has put out. So this is, planet hopping from TRAPPIST-1e. So imagining if you were a person on TRAPPIST-1e, what the other planets would look like. And in fact, just as a fun fact, in developing this poster, they thought very carefully. They actually had someone from a planetarium actually project the constellations, the stars, as it would look like from TRAPPIST-1e. And so the orientation of some of the constellations may look kind of wonky, but that's because they thought carefully about how that would actually be oriented from this particular planet. So I thought that was really cool. And the angular sizes of the planets themselves are also accurate. So yeah, all right. So continuing on, so, again, Mary gave a really nice introduction for this. So, what are the big questions in exoplanet science? And so fundamentally, we want to know, where did we come from and are we alone? And so 2 particular areas of research that I'll be talking about briefly today. The first is kind of my primary expertise, which is understanding weather on extrasolar worlds. So, for Jupiter-sized planets, what's the weather like for these? As I'll discuss, a lot of these planets that I focus on are these Jupiter-sized worlds that orbit very close to their star, closer than Mercury orbits our sun. And so that presents a really unique regime for understanding weather and understanding processes for how an atmosphere moves. And then ultimately, can we then extend those concepts to understanding smaller planets and their long-term climate and whether or not they may be habitable? But of course, everyone's ultimate goal is to find life out there. And so, how do we define habitability fundamentally? What sort of regimes are those? Does habitability lie? What are the biomarkers or biogenic gases that we should try and identify? In searching for life out there? I mean, basically, Earth is kind of our benchmark planet, but of course, there are probably many other ways to sustain and develop life. And so really expanding our imagination and our research capabilities to try and pick out those different facets. Okay. And so since we talked a little bit about transiting exoplanets, I thought I'd just give a little motivation as to what exactly can we learn from these observations. And so this is just a cartoon showing, actually, so the temperature maps that you see for the planet itself are actually from real simulations that I've run, which is pretty fun. So here I'm just showing 3 different phases of a planet, a hot Jupiter, as it were, as it transits in front of its star. And so I should mention, so given that so close into their stars, so within the orbit of Mercury orbiting our sun, we assume that these planets are synchronously rotating or tidally locked. So basically that means that the planet will have a permanent day side, so a permanent side that's constantly facing the star, and then a permanent night side, so a side that's constantly away from the pointing away from the star. And so we can exploit this geometry to extract information about the atmosphere, because we know what we're seeing as a function of time, as the planet transits in front of the star. And so first I'll start at primary eclipse. We're seeing the stellar light that's transmitted through the planet's atmosphere. And so if we subtract off what we know about the star, what we know of the composition of the star, what we're left with is a spectrum called the transmission spectrum as a function of wavelength. And so if we observe that primary eclipse is a function of wavelength, we can see what the, I think Mary had shown an example spectrum, for example, seeing what the atmosphere is made of. Can we measure, is there water in the atmosphere? Is there carbon dioxide or methane or other molecules? So we can look at this for Jupiter-sized planets, and understanding, using these same techniques to potentially look for biomarkers in the future. When the planet passes behind the star, that's called secondary eclipse. And so at that point, we're seeing actually the planet's day side rotating into view, given this tidal locking. And so we're actually seeing the emitted thermal radiation from the planet. So we can actually measure things like the temperature and also the planet's composition. We can also look at molecules if we observe with wavelengths. If we look then throughout its whole orbit, so actually I mentioned thermal phase variations, but you could actually do this at multiple wavelengths. So if we're observing in the infrared, for example, between transit and secondary eclipse, we're looking at the emitted light as a function of time. And so again, given the geometry of the system, we can then invert those observations to then create a temperature map as a function of longitude. So if we're observing emitted flux as a function of orbital phase, that becomes a map with longitude. And so then we can start to actually place some more specific constraints as to how the temperature varies from perhaps the planet's day side to its night side, and how that relates to the planet's dynamics or chemistry or other processes that may be going on in the atmosphere. So they're really powerful. And if you observe these same kinds of phase variations at optical wavelengths, you can actually look, we talked a bit about at these shorter wavelengths, you're probing the planet's reflected light. And so if the planet were to have clouds in its atmosphere, we could then probe those, see the clouds perhaps moving, from perhaps localized on one part of the planet and not the other. And so these phase variations, these phase curves are very powerful observations. Okay. And so now sort of here are the kind of high-level highlights. And so exoplanet science, as I said, is in kind of an era of better data. We're learning quite a lot about many specific planets given how distant they are. So this is an example of a phase curve observation. This is arguably the best, the most high fidelity data set to date. And so here's just an animation kind of visualizing that whole data. And so this was for a particular Jupiter-sized exoplanet, a hot Jupiter called WASP 43b. And so it's orbiting its planet every 19 hours or so, and we were able to collect observations of the planet's atmosphere with the Hubble Space Telescope and the Wide Field Camera instrument. And so this instrument observes the planet's emitted flux between wavelengths of 1.1 to 1.7 microns, which is what the top left panel is showing here. And so what the animation is showing you is it's looping through the different phases of the planet. So as I said, you're observing, the planet as it orbits its star. And so, at a phase of 0.5, you're seeing I believe the night side of the day side of the planet, I'm sorry. And as it rotates, from transit to secondary eclipse and so forth. And so from there, you can use that data to plot this emission spectrum. So as I said, the emitted flux is a function of wavelength. So here we can measure the water abundance, how much water is in the atmosphere as a function of phase or longitude. We can also place constraints on the temperature of the atmosphere as a function of altitude. So that's what the top right panel is showing in this animation. So here the sort of shaded region is kind of showing how well or how accurate that those constraints are, like how well are we measuring it at that particular altitude. And so there's a lot of uncertainty there depending on the quality of the data and so forth. And so at the bottom panel here, I'm showing what's actually particularly powerful about these observations is the observations were made at multiple wavelengths. So if you're making longitudinal observations as a function of wavelength, each wavelength will probe a discrete altitude. And so you're not only gaining information about the planet with longitude, but also with altitude. And so this is what the different brightness temperature maps here are showing. So this is as the planet is orbiting its star, you're probing different regions of the planet. And so at these different wavelengths, you can see that they're brighter or cooler depending on, where in the atmosphere you're probing. And so this is this particular data set was really rife for modeling to try and interpret, okay, well, what can we say about, the composition of the atmosphere? What can we say about the presence of clouds or not, and so forth. Okay. So I would also say we're in an era of more planets. And so I think what's really powerful is now we can not only observe one particular planet, but a large sample of planets. For example, this animation is simply illustrating a sample of 10 hot Jupiters that were observed with a single Hubble Space Telescope program. And so basically now you can start to look at these individual planets and say, okay, well, can we draw trends? Can we deduce any sort of trends in perhaps the cloud properties or the molecular, the chemistry or the molecules that we detect within each of these planets? And so what this actual sample showed is that there's quite a wide diversity in cloud properties for these atmospheres. So these are observations that were done in transit. So we obtained transmission spectra. I have the slide later if you'd like to actually see the data. But fundamentally, it showed quite a diversity in the amplitude of the variations as a function of wavelength, which implied quite a wide range of cloud properties. And what's interesting about this particular population is it probes a wide range of physical properties, so things like rotation rate and the size of the planet or their radii, what their gravities are, and ultimately their temperatures. And all of these things are factors in influencing the planet's weather and ultimately, what clouds would form and how they would persist. And so by studying individual planets together, we can start to draw trends and understand how hot Jupiters as a whole, function. Okay. And finally, we're moving towards smaller planets. And so this is actually, so as I was mentioning, these phase curve observations that were done for a hot Jupiter, within recent years, we've been able to push to conducting these observations for smaller and smaller planets. And so this is an animation of the super Earth 55 Cancri E. So you might have heard of this planet as the so-called diamond planet, given its high density. And so the basic idea, you're conducting those same sorts of observations. And so then you can start, so this is kind of the first hint of what we can start to learn about the thermal structure, the temperature structure of smaller planets and whether or not they may be habitable. This particular one is also on a very short orbital period, so I believe it's, again, on the order of a day. And so its temperature is something like 2000 Kelvin, so way too hot to harbor life on this particular planet. But it's a good way to test our techniques so that when we are, in fact, capable of doing that, we can extend our, the techniques that we've applied and the methods that we've used for observing these sorts of planets for observing smaller ones. Okay. And so sort of more generally in thinking about the future of exoplanet detection, observations, and characterization. So far I've kind of highlighted these hot Jupiters, and we've kind of talked about some of these populations already. But I think as a community, as we start to observe more complex or more exotic atmospheres. So for example, brown dwarfs are kind of our substellar cousins to planets. Some of them share very similar temperatures to some of the planets, depending on where they bracket. And so they kind of serve as a nice comparative benchmark for understanding the chemistry in clouds and various other processes in exoplanet atmospheres, but they require very complex models. Ultimately, if we want to understand what exo-Earths look like and what their weather is like, we sort of necessarily need to increase the complexity of our models, but also the complexity of our understanding. So in the case of hot Jupiters, for example, we know based on our own solar system that Jupiter is comprised primarily of hydrogen and helium. And so we can kind of place those assumptions already as to what the atmosphere is fundamentally made of. But of course, in the case of super Earths or exo-Earths, as it were, you know, they could have a wide range of compositions. They could be water worlds. They could be, you know, filled with carbon dioxide or methane or various other exotic compositions. And so we really need to expand the modeling complexity and what these planets could potentially look like when we want to observe them and understand them. Okay, and I think this is my final slide. Yeah, so just Mary and Brandon already covered some of this, so I won't belabor some of the points, but I just wanted to highlight, you know, where exoplanets and their missions are going. And so I guess, yeah, we already talked quite a bit about TESS, so I won't say too much about that. But again, finding with the transiting exoplanet survey satellite launching in March 2018 to find the nearest, brightest exoplanets. And I should emphasize also, part of the reason for, you know, favoring these brighter stars is that we can also, you know, we can do this follow-up observations from space, but also from the ground. It makes it a lot easier to make these radial velocity measurements, which are primarily done from the ground. And so if we have brighter stars to look at, that makes those observations that much easier to obtain those mass measurements, as Mary was talking about earlier. The James Webb Space Telescope is launching in spring of 2019, and so I like to say it's exoplanet characterization in HD. So we we'll have the benefit of a longer wavelength coverage, and if we have more wavelengths, we're probing more regions in the atmosphere, so we can understand the planet's atmosphere more holistically. And so I think that will be really powerful. I think there are new techniques we can also try to exploit with James Webb, because it'll have a higher resolution and this broader wavelength coverage. So I think that I'm very much looking forward to that. I also wanted to briefly talk about FINESS. So this is a smaller class mission that's currently in its step 1 evaluation, into its step 2 evaluation. And so basically the idea for this particular telescope, this would be another space-based telescope, but it would be a dedicated facility for exoplanet characterization. So this comparative exoplanetology that I was alluding to earlier in the talk, you know, that will be hard to do with Webb to some degree, simply because the time is limited for its operations. And so it would be really nice to have, in addition to Webb, a dedicated facility to kind of complement all of the powerful things that Webb will do. And so stay tuned for that. And then also, I didn't talk about directly imaged planets too much, but the WFIRST will have this microlensing component, but will also potentially be imaging planets. And so at these wide separations. And so this is a different population that you know, missions like Webb and TESS and so forth will probe. And what I find really exciting about WFIRST is we're sort of bridging the gap between these directly imaged planets and these you know, transiting exoplanets / RV planets are kind of already bridging that gap. But WFIRST will kind of help with that in observing some of these RV planets, which we haven't been able to image in reflected light, so we can constrain things like the temperature or the cloud properties, for example, for this range of planets. And so, again, sort of extending the phase space of our understanding of exoplanet atmospheres and processes. And so finally, I'll briefly talk about, so as I think Brandon mentioned earlier, the astrophysics community is kind of well underway in developing, deciding, you know, what's the next future mission, what's the next flagship. And so teams have been formed for these particular decadal concepts. And so basically what's really exciting is, so there are 4 of them, and 3 of the 4 have exoplanet components, and in fact are heavy drivers of the science for these particular missions. And so first I'll talk about HabEx. So HabEx and LUBAR actually are both, will be imaging missions, and so they'll fly coronagraphs, which will image the planet's thermal emitted light separate from the stellar light. And so that's a problem of, you know, you want a planet that's far enough away, you need you need stars that are maybe bright or not too bright, and they're, you know, very complex things in terms of trying to separate the light from a planet and the light of the star. And so HabEx in particular is trying to fly this star shade. So that's what that big sort of petal pedal sail is to its left. So the basic idea would be to essentially block the stellar light before it ever hits the telescope. And so that would make it even easier to image Earth-sized planets that are orbiting different stars. And so that's one particular concept. LUVOIR is basically an all-purpose kind of a super HST, so it will be a very large telescope operating over somewhat similar wavelengths, but with exoplanets being a big driver. And the Origin Space Telescope, which I'm involved in, will actually be observing transiting exoplanets primarily from 5 to 30 microns, which is kind of unprecedented for exoplanet observations to date. And so all of these have very interesting and exciting components, TBD to see which gets selected, but I think exoplanets has quite literally a very bright future. So I think that's all of my slides. And I'm happy to take questions or however, whatever's easiest.
Yeah, great. Let's see, I'm gonna.
Shall I stop sharing my screen?
I'm gonna share here and we'll. So do people have questions? You can unmute yourself if you would rather just ask it by voice, or you can type it in the chat box. We'll give a little time. And it can be questions generally about exoplanet science or specifically about characterizing the weather on exoplanets, as Tiffany just talked about. Any questions?
Thanks, Brandon. Yeah, I should have mentioned the fourth one, but.
Yeah. Yeah. So, well, people are thinking of a question to type in the chat box. I have a question, Tiffany, which is, so you had this thermal map. I think that was of WASP 43 too. Yeah.
WASP 43. Yeah.
Yeah. So, could you, in kind of more everyday terms, I mean, it looked like how would you characterize? Is it windy because you have this day and night? What's going on? If you were to be, dive into that atmosphere, what would you experience?
Sure. Yeah. So it's very extreme weather, and so given this day-night forcing that arises from this sort of tidal locking, it induces these essentially these waves that produce this very strong super rotating jet on the planet. And so this is very akin to, the super rotating jet we see on Venus, except the speeds of this jet are on the order of kilometers per second. So very, very fast, likely supersonic, faster than the speed of sound. And so the environment would not be, not be kind, let's say. And so for this particular planet, I think my simulation showed predicted winds of, 4 kilometers per second, something like that. And so, yeah, pretty extreme weather, and definitely unlike anything we see within our own solar system.
Right.
How far away is that planet?
I don't remember off the top of my head. I can probably see.
Do that out.
Come on, Wikipedia.
Yeah.
Like Wikipedia will give me the answer, but no. Let's see. I think
Are we looking at like tens of light years or hundreds or more?
It's probably I think tens. I mean, let's see.
It's a fairly bright star.
Yes, it is
So it's probably in the hundreds of light years, I would say, or tens, not thousands.
Not more than that.
Yeah, no.
But the fact that we can figure out the weather on planets as far away as that is another one of those things that will blow people's minds.
Yes, absolutely.
I mean, it does mine.
Yeah.
The precision and the methods are amazing.
Yeah.
All right. Well, if anybody does have additional questions, here we go. Here's one.
Roughly 200 light years. Sorry.
Okay, so Bridget is asking, have you ever been in a situation where you spoke with younger people, like 8 to 12 years old? I'm wondering what kinds of questions they asked, what they were most interested in.
So I haven't, I would say I haven't given a ton, but JPL has outreach events and various things where the public can come and ask questions. Um, let's see, what kind of questions have they asked? I mean, usually they're kind of centered around demos. And so I guess, they ask things like, what are these planets made of? What does life look like? What kind of, trying to think if there are any kind of questions that kept coming up. But yeah, I mean, I think they were fairly, basic questions, but I think they're definitely captured by the fact that they're super far away and that we can, I think they draw a lot from the transit method, and they kind of understand eclipse, given, eclipses within our own, the solar eclipse, lunar eclipse, and so forth. So they have kind of some, sense of what that's like. And I mean, certainly with the TRAPPIST system, there's quite a lot of attention on that. And so I think at the last JPL open house, it was kind of the focal point of our booth, which I think was a good thing. Yeah. I'm wondering what this might look like in the 2030s. I guess in terms of exoplanet science, I'm assuming you mean, say when they grow up. If this will, yeah. So actually, I didn't answer the poll about, and we can come back to, whether or not, when I think we'll find life outside of the solar system.
I love that that's a when.
Yeah, right, exactly. I think it's not an if, I think it is a when. I mean, I'm perhaps less optimistic that it'll happen during my lifetime, but I think, the thing I often say is, nature has really surprised us. I don't think anyone expected to find Jupiter-sized planets, orbiting so close to these stars. That completely revised our entire understanding for how planets form and evolve. And so I could definitely imagine a scenario where the same could be true for, perhaps one of these TRAPPIST planets that we observe with Webb. They may give quite surprising results that we didn't yet expect. So, I'm perhaps more pessimistic, but I'm willing to be surprised, I guess, with that regard. I also am excited for what direct imaging will give us, because I think right now, not even the problem, but I guess the challenge is, again, it's really hard to separate the light from, directly image and separate the light of a star from its planet that could be really tiny. And so they kind of have very low numbers at this point. I think we know maybe 10 or so directly imaged planets that we can kind of follow up with other facilities, and they're more Jupiter sized than anything. And so I'm really excited to see with potentially one of these future missions finding and characterizing some of these smaller planets.
We have one more.
Yeah, there's one more question. We'll answer this one, and then we know we're a little bit short on time here, so we'll move on. If you do have more questions, feel free to put them in, and we can try and answer those on the forum on the Moodle a little bit later. Yeah. So just to read it out loud for everyone, do you think there is any chance that we will discover something that alters, quote, life as we know it, quote, by extending our definition of life?
I think so. I mean, I think life finds a way, as they as they always say. I think it's very true. I mean, especially on Earth, we find life in the deepest depths of our ocean, where little microbes don't even see any sort of sunlight. And so, if you think photosynthesis plays a role in life's evolution, I mean, the life that we see at the bottom of the ocean is, defying that kind of assumption. And so one thing actually I find really exciting about the search for life is that, we're conducting the search within exoplanets, but we're also simultaneously, and sort of in a complementary sense, doing the same kind of search within our own solar system. So on the icy satellites like Europa, or perhaps an early Earth type similar atmosphere and Titan. And so, these kind of searches are going on simultaneously, with very different techniques, and obviously with their own pros and cons. And so I think to me, it's kind of exciting to see kind of which one will win out, or not even win out, but which one, perhaps will find the greatest evidence for life first. And so I think it's very possible that we'll have to, extend how we think life can arise and evolve within both of these searches. Yeah.
All right. Well, thank you again, Dr. Kataria, for helping us out today.
Sure. Happy to be here.
And would you be up for answering a few of these other questions that might come through? We can forward them on to you.
Sure, yeah, not a problem. Happy to do.
That would be fabulous. So I know we are a little bit past time here, so I'm going to keep the discussion of the resources brief for the moment. But I do, again, encourage you to explore some of these, but I am going to show you a couple really quickly here. And the first one got mentioned a long time ago, but it's this fabulous, and I'm going to share my screen here because I have it open, this fabulous resource called Eyes on Exoplanets. And it gives you a chance to look around any particular star that we found an exoplanet on and learn a little bit of information about it. You can see what the star might look like. You can see, oh, some planets in the system are not shown to do insufficient data, so we can only do it with particular ones. We've mentioned the TRAPPIST one a couple times, so let me try and pull that one up real quick. Oops, click on TRAPPIST-1, and we'll get a little zoom into where it is. And when we get here, you're going to see, oh, and my system does not seem to be working right now. Normally, you're going to be able to see the planets orbiting around the star. You're going to be able to figure out information about how long it takes to get there. You can, see what it's possible to look at the sky from the Earth and take a look at where all of the planets are from any particular point on Earth. You can see that big glowing thing. That's where Kepler's been staring, and it has found so many planets in that particular area. But this is a really great resource to play around with. There's both a computer mode and a kiosk mode. I know there are a number of museums and science centers that have this up as a resource, or excuse me, as an exhibit in their museum. So that's another option. Next, I'm going to jump back to the show. And, oops, the participant thing is in my way. There we go. So there are other resources. Microobservatory, many of you folks are familiar with Microobservatory, having worked with it in the past. But there's actually now a planet search portion of it where you can go ahead and detect planets on your own. You can control them robotic telescopes and ask them to study a star that we know has a hot Jupiter around it, and over the course of a night you can see light curves from actual data that you're collecting overnight, assuming the weather is cooperating with you. So it's a chance for people to participate and get connected to that actual data, which is always very, very powerful, as I was mentioning in the chat earlier. If you go in, create your account, set a username and password, you can sign up as a do-it-yourself planet searcher. There are 360 images of some exoplanets. This is the surface of TRAPPIST-1D, artist impression, of course. We can't actually see what it looks like from the surface of those planets yet, hopefully. But you can look at this on a computer and drag the picture around with a mouse. You can put it up on a phone and actually look around you and look up in the sky and see the other planets there. And you can also set it up with Google Cardboard, which is a really exciting opportunity for a lot of people. Exoplanets.nasa.gov has a lot of other things. You saw the transit animations earlier. There are interactives where you can try and make your own planet. Dr. Kataria showed that travel poster. There are a number of different travel posters of visiting other exoplanets on there as well. So all sorts of things. It's a really fabulous site. We've mentioned the Universe Discovery Guides a couple of different times. There is one completely devoted to exoplanets, the April edition. The link is in here again if you want to go visit those. And the last thing, maybe not the last thing, I'm going to mention there's a coronagraphy activity that we developed here at Space Telescope earlier this year. Chapter, and it's an actual in-person activity that you can build out of cardboard and popsicle sticks and light bulbs, and people can actually see how a coronagraph can help you detect exoplanets. And that's that method of blocking the star's light so that those exoplanets, which might otherwise be overwhelmed by that star's light, become a bit more visible. This is something that we've just piloted. We haven't even taken that piloting stage to working with an actual proper audience. So if you're interested in doing something like this, if you're interested in modifying it, if you've got questions, we want to know, and we want to see how this might work in the real world out there. And the last thing, this is from some of the resources that were created under Kepler. It's an activity for a human-powered ORI. So basically, for people to become part of their own little solar system. It's a fun activity that gives a kinesthetic chance to get involved with the mechanics of exoplanets, or our solar system as well. We will be sticking the actual activity up on the Moodle, I believe, because the activity keeps moving around on the internet and it hasn't been in a stable location, so we can't quite find that link for you today. But we've got a digital copy, and we'll upload that so you can all access that easily.
Already there, Tim.
Awesome. Erica's already taken care of it. So on that note, I'm also going to pass it on to Erica to talk about what's upcoming. Oh, yeah, and this image, I just want to point, because I love this image, it's from the Keck telescope, but it was put together by Nexus, I think is how it's pronounced, which is a NASA-supported group to promote exoplanetary science. And this is a series of images put together of some directly imaged exoplanets with a coronagraph. That's that big black thing blocking the star's light in the center. But those are actual planets orbiting another star. So, Erica, take it away.
All right, I'll do this quick as a quick review of where we are. And believe it or not, we only have one webinar left. One more in our series of understanding what NASA's up to and how the universe works and how we got here. So next, in 2 weeks, on November 8th, we're going to continue on answering the question, are we alone? We're going to discuss the topic of finding life. So we're going to go a little farther into that habitability of these exoplanets. Go to the next slide, Tim. So for the following 2 weeks, we want to continue talking about what program models you're beginning to formulate on the Moodle. We know we have a couple questions we have to get to, and we'll be answering them within the next day or so. Cheyenne, can't remember if you're on today, but we've talked and we're going to get back to you. So keep asking questions there. Let us know what program models you're thinking of, what resources could be helpful for you. We're here to help you find those and kind of give you any feedback we can. One more slide. All right. So just as a quick reminder, the applications are going to open on November 9th. We're going to do a quick application Q&A on the 15th. So that's the week following our last official webinar. We're going to have an hour for you to come online, ask us questions, get feedback on your proposals so that they can be the best that they can be. The application deadline will be December 14th, and then we'll let you know about our selection on December 18th. So that's our big reminders. We're almost done.
Clarification there, Erica. You said 14th, and the slide says 4th?
4th. Yes, thank you. Read quickly there.
All right, December 4th.
The slide is correct.
All right. So thank you again, everybody, for joining us. I'm going to stop sharing. But we hope to see you again in 2 weeks. We hope you're all able to contribute to the ongoing discussion on the Moodle. And if you have more questions about exoplanets, put those up there as well. But I believe that's it. Mary, anything to add before we close today?
No, we'll hope to get some more discussions going on the online portal about plans for how to apply these things, and how you might use some resources to create a program or an exhibit or an event. So hopefully you'll see some good ideas there in the resources that will spark your imagination. Great.
Thank you, everybody, for attending.
Thank you, Tiffany.
Bye, everyone.